Hello, everybody. This is a video about the assignment, Interpret Change in Exponential Models with Manipulation. All right, I didn't care for the job I did on Zoom, so I'm going to redo it here and try to do a better job. It's easier for me to just do it as a recording than it is live. So, all right, so let's look at this first problem. It says, on the first day of spring, an entire field of flowering trees blossoms. On the first day of spring, an entire field of flowering trees blossoms. The population of locusts consuming these flowers rapidly increases as the trees blossom. The relationship between the elapsed time t in weeks, okay, so this is in weeks, since the beginning of spring, and the total number of locusts, which is n of t right here, is modeled by this function. Complete the following sentence about the rate of change of the locust population. Round your answer to 2 decimal places. Notice these are perfect squares. So right off the bat, when you do these problems, they're going to give you numbers like that are perfect squares or perfect cubes, typically, right? So one of those two, perfect squares or perfect cubes. 49 is a perfect square because 7 squared is 49, and 16 is a perfect square because 4 squared is 16. All right, complete the following sentence about the rate of change of the locust population. Round your answer to 2 decimal places. The population of locusts gains 3/4 of its size every so many weeks. All right, so here's the idea. We have the function n of t equals 300. So originally there's like 300 locusts, right? And this is a growth rate, right? So because this value of this fraction is bigger than 1, we know that the population of locusts are growing. Okay. It wants it as 3/4. Now, if I take the square root of both of these, then I can get 4 on the bottom. So I'm going to rewrite this as n of t equals 300 times square root of that's 7, square root of that's 4. So to get it back to 49, you have to square it, right? So 7 squared is 49, 4 squared is 16. And it gets multiplied to that t that's already out there. So that's the t. Okay. So 7/4, let's look, 7/4 is 4/4 plus 3/4, right? Or if you like, 1 3/4. So this is a growth rate of 3/4. It's growing, it's adding like 75% every cycle. It's adding 75% when this comes out to equal 1, right? So in other words, we need 2t to equal 1. So if we want 2t to equal 1, t is going to have to be a half, right? So half a week. So every half of a week, it increases by 3/4. All right, let's try another one of these. Kylie sent a chain letter to her friends asking them to forward the letter to more friends. The relationship between the elapsed time t in hours, so this is in hours, since Kylie sent the letter, and the number of people P of t who received the email is modeled by this function. Complete the following sentence about the hourly percent change in the number of people who received the email. Round your answer to the nearest percent. Okay, so in this situation, let's do it over here. Got a linear exponent, right? So P of t equals 1.09 raised to the 6t plus 25.5. Okay. Now, whenever you have a linear exponent like this, you can break this up into two terms. So this could be 1.09 raised to the 6t times 1.09, that's times, raised to the 25.5. Right now, 25.5 is simply just a number, right? So let's see what that is. 1.09 raised to the 25.5 is really 9. So, and I'm going to write that first here. So I'm going to do P of t equals this, all of this is just 9 times. Now what I want is that just to be a t. So I'm going to go ahead and raise 1.09 to the 6th power. Right, so it's going to be 1.09 raised to the 6th power is about what, 1.68? 1.68 to the t. All right, so all I did to get this value is I raised 1.09 to the 6th power. Now I've got a 1t, which is what I need. And now I can see the growth rate is 68%, right? So every hour there is a 68% addition. And it's addition because this value is bigger than 1, so it's growing. And, you know, common sense tells me her email scheme has to grow. The number of total emails read is just going to keep going up. So 68% addition to the number of people who receive the email. All right. Okay, let's try another one. I'll do this one down here. On the first day of spring, an entire field of flowering trees blossoms. The population of locusts consuming these flowers rapidly increases as the trees blossom. The relationship between the elapsed time t in weeks since the beginning of spring and the total number of locusts, n of t, is modeled by this function. N of t equals 300 times 9 to the t. Okay. So that means that every, week, this gets multiplied by 9. The number, however many locusts there are, goes up 9 times week to week, right? All right, so this says the number of locusts is tripled every what? Well, notice 9 is a perfect square. So I can change this to 303 squared t. And that 2 can come out there, so that's 300 times 3 to the 2t. All right? So what I want, if I want to know, the question is, it triples. So now I've got it to where it triples, but this is going to need to be 1. So 2t is going to need to be 1, which means t is going to need to be a half. So therefore, this is 1/2. All right. One more. So we've got m of t equals 1.34 raised to the t over 6 plus 4. Okay, now you know automatically you're going to want to break that up, right? So that's going to be 1.34 to the t over 6 times 1.34 to the 4th. Okay. The question is every day. So t is in days, right? I don't know what's this about. Ocean sunfish are well known for rapidly gaining a lot of weight on a diet based on jellyfish. The relationship between the elapsed time t and days since the ocean sunfish is born and its mass is modeled by this function. All right, so every day the mass the mass of sunfish is multiplied by a factor of, okay, so we have this fraction this time. So I'm going to break that up into 1/6 times t. And then this is just some number for the initial amount of sunfish, right? So I'll just calculate that real quick. It's not really necessary to do this, but to avoid confusion, let's get rid of that exponent. So that's about 3.22. Okay. Now I can go ahead and raise this value 1.34 to the 1/6 power. And then I'll just have t out there, right? So what I'm going to do is basically take that 1/6 inside and usually this value goes in the front. It doesn't have to go in the front, but that's just generally how you would see it, so I'll put it right there. All right, so now I just need to raise that to the 1/6 power. So 1.36 raised to the 1/6 power is about 1.05. So this would be 3.22 times 1.05 raised to the t. Okay, so now we can see that it's being multiplied by a factor of 1.05. So I'm just going to put in 1.05. Okay, and that's it. Hopefully that's a little clearer. I didn't feel like I was very clear in this Zoom meeting. So if you watch this, hopefully it helped a little bit more. Thanks so much for watching and have a great day.